Okay, so we're going to look at the Pythagorean theorem as it applies to some measurements for three-dimensional objects. Suppose I have a box, a rectangular box, which I've drawn here above, and I'm interested in how long a diagonal is that runs from vertex A all the way down through the inside of the box to vertex B. What I'd like to do is find a right triangle for which that length AB is a leg or a hypotenuse. And there's not one directly in the figure right now unless I add an auxiliary segment somewhere. For example, if I were to then add a diagonal across the top of the box here to T, and then look at triangle ATB, note I'm going to have a right angle here. AT is going to be perpendicular to TB. And now I've got a right triangle, ATB, such that I have my desired length, AB, that I'm looking for as a hypotenuse. So suppose I'm given some lengths here. Suppose I'm given CD is 3, DE is 4, and the height of this box is 5. What I'm looking to find, again, is AB. So the first thing I note is I'm going to draw that triangle out down below that I'm looking at, and I'm going to label it. Here's T, here's A, and I want to find AB, and the only thing I know is TB is 5. If I look at the top of the box, though, I'm going to note that that side AT is a diagonal of the top rectangle. And I'm going to draw that triangle out separately as well. And I note that its dimensions are, from this being a rectangular box, I've got 3 and I've got a 4 here and a right angle here. So a 3, a 4, 3, 4, 5 right triangles. That length is 5. And that length, again, is segment AT in that rectangle that's in the top of the box. So that's a 5 here. And then I note by Pythagorean theorem, or certainly remembering my special right triangles, the length of that hypotenuse in my three-dimensional triangle is going to be 5 root 2. Okay, so here's another problem. Suppose I have a triangular pyramid. That means the base is a triangle, and the base here I'll have be ABC up to a vertex up here at E. And I'm interested, supposing I know that this is a triangular pyramid, all the edges have length of 6. So the lengths of all the base edges are 6, and the lengths of all the edges coming up to the peak of the triangle, or to the pyramid, are 6. Suppose I want to find the height of this pyramid. That's the three-dimensional distance in there from the vertex E up top to the center of the base, and let's call that T. I want to find that length ET, and again note that's a three-dimensional length from the vertex of the pyramid down to the base. Right now that length does not appear in a right triangle, so what I need to do is get it in a right triangle by adding an auxiliary segment. Now there are different ways to do this. I can get there different ways, but I'm going to get there by drawing BT. So I then look at triangle ETB and see what I have. I want to find ET, no pun intended, H, and I got the hypotenuse here is 6. I don't have this length down here, BT. And note it's a right triangle because if I drop, I'm looking at the height of the pyramid to be the altitude from E to T. So continuing here, if we can find TB, then we're all set and we'll be able to use Pythagorean theorem to find H in this triangle. To find BT, I've got to look at where it is relative to this base, the whole base triangle. I'm going to try and find BT by looking at that two-dimensionally now. So if I draw that triangle out separately, I'm going to draw actually the base out separately first. This is my base of my pyramid, A, C, B. and I'm looking at BT is right here. Now we said if we drop that perpendicular down to the center of the base, I know that all of these segments are going to be congruent. If those are congruent, then I've got some isosceles triangles in here, and remember each angle in an equilateral triangle is a 60-degree angle. So if I do that, then I'm looking at some 30-degree angles in here all the way around. These are all going to be 30s and all congruent. And I'm interested in finding this length here, and I know that the base edge here they're all 6. So if I were to look at drawing, say, a altitude down to here, I would have 3 and 3. That 3 is going to be opposite 60 degrees. So if 3 is opposite the 60, I'd have to divide by root 3 to get to opposite the 30. So to find this side here, that would be 3 over root 3, which turns out to be root 3, and should make sense to you. So if I look at this triangle here, now if I were given opposite the 60, if I were given that as 3, and I've just found opposite the 30 to be root 3, multiply root 3 by root 3 and you'll get 3. So then opposite the 90 is going to be 2 root 3. So this is going to be 2 root 3 here. So now I'll go back. That's the length I wanted BT, is 2 root 3. So now I can just go ahead and use Pythagorean theorem to find that length of h. 2 root 3 squared plus h squared equals 6 squared, or 12 plus h squared equals 36. H equals the square root of 24. H equals 2 root 6. So note I had to use 2 different triangles here. I had to use the 3-dimensional one to get, that's what I'm ideally using to get h, but then I had to use another group of triangles in the base of the pyramid to get this missing side BT. And note I drew out a whole bunch of triangles to help me get this process done.